Each year, the world produces more than 200 million tons of glass, a material that, while it may seem common and ordinary, is made from one of the purest sands on Earth. But how is it possible for grains of sand to become the glass we all use? To find out, we're heading inside the largest glass factory in existence to see the process. How long do you think glass has been around? The history of this material goes back thousands of years, when ancient artisans in the Middle East discovered by accident that heating sand with other minerals near a campfire formed a solid, clear substance. Around 3500 BC in Mesopotamia, it was used to make beads and basic jewellery. But it wasn't until the Egyptians, about 2000 years later, refined the technique to craft cups and containers. Over time, the Romans expanded its use to windows and bottles, revolutionising architecture and food storage. In the Middle Ages, Venice became the centre of glassmaking, with jealously guarded secrets, including formulas for colours and clarity. The Industrial Revolution brought machines that sped up the process, making mass production possible. Today, in massive modern plants, that ancient alchemy is combined with cutting-edge technology to create the glass products we use every day. But how is it done? It all starts long before we see a bottle or window, with silica sand. This material makes up as much as 70% of the glass mixture, and not just any sand will do. Beach sand won't work because it contains too many impurities. What's needed is an almost perfect variety, with at least 99% silica. To get it, huge excavators, machines as large as a two-storey house, remove entire layers of soil and rock in open-pit mines, mostly in Midwestern regions. Each of these giants moves up to 100 tons per trip, aided by enormous trucks that navigate the mine's internal roads like arteries in a living organism. Once the sand deposit is reached, controlled explosives are used to fragment the rock. Nothing is left to chance. Techniques are applied to minimize dust, and high-pressure water systems help reduce environmental impact. The resulting fragments are transported to a nearby plant, where jaw and cone crushers turn them into fine, uniform grains, just a few millimeters in size. This detail is vital. Any impurity, such as clay or iron, can ruin the transparency of the final glass. At the factory, more than 5,000 tons of sand are processed each week. To ensure a constant supply, trains and trucks arrive regularly from the mine. But before it can be used, the sand undergoes a thorough treatment. First, it is unloaded into giant hoppers that feed vibrating screens. These sieves filter out everything from large stones to the finest particles, starting with meshes of 30 holes per square inch. Next, it enters washing chambers, where powerful jets of water, driven by 200 horsepower pumps, clean the sand at an impressive rate, more than 220 tons per hour. Technology works its magic here. Centrifugal spirals separate denser materials like tiny metal fragments, while magnetic separators remove even the smallest traces of iron. It might seem insignificant, but even 0.1% iron could give glass an unwanted green or brown tint. Once clean, the sand goes through drying. It is fed into massive rotary kilns at 150 degrees Celsius, where moisture slowly evaporates. Sensors monitor the entire process to ensure the water content is nearly zero. This step can take hours, but it's essential. If any water remained trapped, bubbles would form in the glass during melting. Finally, the purified sand is stored in silos or packed into 1-ton bags, ready for the next step in production. And here's the key. This level of purity not only guarantees perfectly clear glass, but also gives it the strength needed to withstand extreme temperatures. That's what allows it to be used in everything from food containers to windows that endure years of sun, cold, and changing weather. Once at the main plant, the most delicate part begins, transforming the purified sand into glass. To achieve it, pure silica isn't enough. Other ingredients are needed, working as chemical allies in the recipe. First comes sodium carbonate, derived from common salt. Its job is to lower the melting point of silica from about 1,700 degrees Celsius to around 1,500 degrees Celsius. It may seem like a small adjustment, but it represents a huge energy saving. Next is calcium carbonate, obtained from limestone, which strengthens the structure of the glass and prevents it from dissolving when in contact with water or acids. And if colour is desired, the formula is enriched with metallic oxides, cobalt for a deep blue, chromium for a vivid green, or selenium for a rich red. This is how the batch is born, the base mixture that will give life to glass. This mix isn't prepared by hand, but in industrial mixers spinning at 1,000 revolutions per minute. Each batch can hold up to 50,000 kilos of perfectly homogeneous material. From there, conveyor belts with weight sensors carry it to the heart of the factory, the melting furnace. This giant, made of refractory steel and powered by natural gas, never rests. It operates 24 hours a day, reaching 1,650 degrees Celsius, hotter than volcanic lava. Here, silica transforms into an amorphous, fluid network, similar to glowing honey. For about 24 hours, the mix melts while technicians in protective suits monitor every detail. They use thermocouples to measure temperature precisely and adjust oxygen flow to improve combustion while reducing carbon dioxide emissions. But it's not ready yet. The molten glass must release trapped gases to avoid bubbles or flaws. This refining stage lasts several hours and is aided by mechanical stirrers that keep everything perfectly uniform. Once purified, the glass is ready to be shaped into everyday objects such as bottles. To achieve this, it's channeled into automatic blowing machines, capable of producing up to 500 bottles per minute. The process is fascinating. Small portions of molten glass, called gobs, are cut at about 1,100 degrees Celsius. Each gob drops into a preliminary mould, where a jet of compressed air expands it into an initial form known as a parison, a hollow tube with a neck. That parison is then transferred to a final mould, where another burst of air inflates it against the mould walls, giving it its final shape in seconds. The moulds, made of cast iron and coated with graphite, prevent the glass from sticking and stay cool thanks to a circulating water system. To ensure perfection, laser sensors synchronize every movement and check the thickness and volume of each bottle. The technique is so versatile that, with simple adjustments to gob size or air pressure, manufacturers can create anything from 50 milliliters medicine jars to 1 liter soda bottles. Fresh out of the mold, the bottles still glow a fiery red. They're around 600 degrees Celsius, hot enough to remain malleable but extremely fragile. At this point, even a light touch could deform or crack them. That's why high-precision robotic arms equipped with machine vision step in. These robots not only pick up each bottle gently, but also adjust their position in milliseconds so they move perfectly aligned. From there, they travel along a metal mesh conveyor designed to withstand high temperatures and let heat escape evenly. This conveyor takes them to an annealing tunnel, a horizontal furnace about 50 meters long. Inside, the temperature gradually drops, from 600 degrees Celsius down to room temperature in about 30 minutes. This controlled cooling is no minor detail. It prevents the glass from building up internal stresses that could make it shatter with the slightest temperature change. Without it, a perfectly formed bottle might crack on its own hours or even days later. The tunnel is divided into multiple heating and ventilation zones, each precisely regulated. Computers and sensors work together, adjusting fan power and heat in real time to maintain an exact thermal gradient. Here, materials science meets automation to ensure the durability of the final product. Once cooled, the bottles move on to automatic inspection. High-speed cameras, capable of capturing thousands of images per second, scan each piece in 360 degrees, detecting flaws almost invisible to the naked eye. Microscopic cracks, trapped bubbles, or variations in thickness. Even an imperfection, just a few microns wide, can weaken the glass. Artificial intelligence systems analyze those images and classify each defect instantly. Up to 5% of the production can be rejected at this stage, but nothing goes to waste. Defective bottles are sent to the recycling area and reintroduced into the production cycle as raw material. The neck of each bottle is also carefully checked. Mechanical probes measure its diameter and ensure that the seal will be perfect. This is essential. Even the slightest flaw in that area could mean caps won't fit properly, compromising the product's airtightness. Alongside container manufacturing, the plant also produces flat glass, used in windows, screens, and solar panels. Here, recycling plays a leading role. Up to 80% of the mix can be cullet, crushed glass recovered from recycling facilities. This strategy not only reduces raw material extraction, but also cuts energy use by about 20%, making the process more economical and sustainable. The recycled material is crushed, cleaned, and mixed with fresh sand before entering furnaces similar to those used for bottles. However, the shaping method is different. The float process is used, where molten glass is poured onto a bath of liquid tin at around 1000 degrees Celsius. Thanks to the difference in density, the glass floats on the tin and spreads into a continuous sheet, perfectly level, with a thickness ranging from 3 to 19 millimeters. The surface of the tin, pure at 100%, acts as an invisible mold, giving the glass a perfectly smooth and uniform face. This eliminates the need for later polishing, a breakthrough that revolutionized the industry in the mid-20th century. As the sheet moves forward slowly, about 1 meter per minute, side rollers guide its width, which can reach up to 3 meters on some lines. It then passes through cooling zones that solidify the glass without warping or waves. At the end of the bath, another 50-meter section, the sheet reaches about 600 degrees Celsius, a temperature high enough to maintain stability before being cut into panels ready for distribution. Precision cutting is a key step. Diamond-coated wheels or lasers score the glass without creating splinters or microcracks. Robotic arms with machine vision guide the tools to the exact dimensions required by the customer. From 2 by 3 meter window panels to much larger formats for architecture. Once cut, the edges are too sharp to handle safely, so they move to progressive polishing machines. These use abrasive wheels, from coarse to ultra-fine, to remove sharpness and leave smooth, safe edges. To prevent heat from damaging the glass, the process is constantly cooled with recirculated water, which also saves resources. Next come the quality tests. Entire panels are subjected to impacts with steel balls or to pressures simulating extreme winds and accidental blows. In the case of tempered glass, the goal is that, if it breaks, it shatters into tiny fragments, like a spider web, reducing the risk of serious cuts. This effect is achieved during tempering, where panels are heated to about 620 degrees Celsius and then cooled rapidly with high-pressure air. The result? Glass up to 5 times stronger, essential for cars, facades, and skyscrapers. With the glass ready, automated packaging takes over. For bottles, robots with suction cups lift full rows of 24 units and place them on pallets, separating layers with protective cardboard. Then, machines wrap everything in plastic film under controlled tension so nothing shifts during transport. Each batch receives a QR code, ensuring full traceability from the factory to the point of sale. For flat glass, panels, which can easily weigh over 200 kilos each, are stacked vertically on metal racks with foam spacers to prevent direct contact. From there, they're loaded into shipping containers, ready for export worldwide. All of this happens in plants designed for efficiency and sustainability. Waste heat from furnaces is reused to preheat the initial mix, cutting fuel consumption. Lighting runs on LED systems, and many facilities incorporate water recovery and emission control systems, significantly reducing their carbon footprint. And that's how sand becomes the glass we use every day. What did you think of the process? Let me know in the comments. If you enjoyed the video, click the like button and don't forget to subscribe to the channel. On the screens you'll see next, there are more videos you might enjoy. Go ahead and check them out. See you next time.